Okay, welcome class for this session. Today we will discuss about the frequency domain interpretation of a LQR system, and this we will do for the linear time invariant system. In the previous class we have discussed about how we can develop the optimal control law for a time varying and the time invariant system. This optimal control law can be determined if we can find out the solution of a Riccati equation. So, for time varying case, my Riccati equation is a differential matrix Riccati equation, and for the time invariant case this is a algebraic equation, which can be in both case this is a nonlinear equation. For time varying case it can be solved using the numerical technique, and for analytical solution also we have seen how we can determine the value of the Riccati coefficient P by the different ways. We have also discussed about the stability of the LQR system, and we have shown for time varying as well as the time invariant case, in both the cases my system is a stable system. Whatever be the condition of the matrix A, but the closed loop system A minus Bk always will be a stable system. So, today we will discuss about the frequency domain interpretation, means what is the, if we will have the frequency response analysis and we are willing to find out the gain margin and the phase margin of the system, how we can find all this. So, this we are taking for the linear time invariant system. So, we will consider a LTI system as x dot t equal to AXT plus BUT. Objective is we have to determine the optimal control law UT, which will minimize the performance index J as 1 by 2 integral 0 to infinity x prime qx plus u prime ru dt. So, if we will solve this problem, we know we can find the optimal control law, which is minus R inverse B prime P x t, where R inverse B prime P we call the K. So, this is minus K x t, where P is the solution of my algebraic Riccati equation, which is P A plus A prime P plus Q minus P B R inverse B prime P equal to 0. So, if I can solve this algebraic Riccati equation to find the P, I can find out the U, which is R inverse B prime P, R I know, B I know, P we already have determined. So, I can find out the K. So, if I will apply the control law U equal to minus Kx, so this is A x t minus B k x t. So, A minus B k, A minus B k R inverse B prime P is nothing but my closed loop matrix, and we already have shown that in this system whatever be the matrix A, my closed loop system always is a stable system. So, now if we will see the characteristic equation of my closed loop and the open loop system, my open loop system is x dot t equal to A, which is constant, x t plus B u t, and u t is nothing but minus R inverse B prime P x of t, and which nothing but we are saying this is u equal to minus k x of t. So, my characteristic equation for open loop system for open loop which I mention as the A naught, it is nothing but my Si minus determinant of Si minus A. So, this is the characteristic equation for the open loop, and what is my closed loop system? My closed loop system is x dot t. If I will substitute u into this is nothing but A minus bk x t. For closed loop system, my characteristic equation is nothing but Si minus, in place of A I have my A minus Bk matrix. So, determinant of this must be equal to 0. So, that we are saying here, if this is the open loop characteristic equation, determinant of Si minus A, and for closed loop this is delta C, this is Si minus A plus Bk, or we can write Si minus A minus Bk in bracket. So, this equation can be written in the form as determinant of Si minus A, the whole determinant must be 0, and this is my delta closed loop. So, this closed loop characteristic equation. So, what we have done, if I will expand this as Si minus A plus Bk. So, I am taking these two as outside. So, if I will take Si minus A outside, so this is I plus Bk Si minus A inverse. So, if I am multiplying this, this is Si minus A, this will become unity, and I get the Si minus A plus Bk. So, this closed loop equation I can further simplify. So, I am writing this closed loop characteristic equation as, so in place of straight line determinant, I am writing the determinant of say what is this? This is the determinant of this matrix and determinant of this matrix. If I will expand this, I can write determinant of Si minus A multiplied with the determinant of I plus Bk Si minus A inverse Si minus A inverse, and this is nothing but equal to my 0. So, for the second determinant we use the identity determinant I plus Mn is equal to determinant I plus Nm. So, if you will use this identity with considering K Si minus A inverse as my N and B as M. So, in this if you will apply this identity determinant I plus Mn, so I can write my closed loop characteristic equation as determinant Si minus A multiplied with determinant I plus K Si minus A inverse B. This is equal to 0. So, this closed loop matrix we are writing as determinant of I plus Bk Si minus A inverse into Si, or this is my closed loop characteristic equation, where delta 0 we are saying Si minus A. So, this Bk we have written as K Si minus A inverse B. So, this equation here delta 0 is nothing but my Si minus A, this I am expanding as determinant Si minus A determinant I plus K Si minus A inverse B. Now, if you will see the S domain block diagram of the system, so this is my plant and plant is nothing but my Si minus A inverse B. So, this is my US, this will be nothing but my XS, here we are adding the K which is nothing but R inverse B prime P, this is given here with negative sign, and this we can write as capital RS, which is nothing but we have taken as 0. In LQR system my RS is 0. So, I can represent the S domain block diagram by this. So, my overall block diagram is Si minus A inverse B, K multiplied with the K, which is giving me nothing but the RS value. So, this is the relation between RS and XS. So, my if we will see K Si minus A inverse B, if I am multiplying this, nothing but giving me the loop gain, and if I am writing the characteristic equation, this is I plus K Si minus A inverse B, this is known as my return difference matrix. So, in frequency domain I can represent my LQR system as given by this block diagram, which is similar to as given here with this block diagram, where K Si minus A inverse B is nothing but my loop gain, and if I am writing I plus K Si minus A inverse B, this is my return difference matrix. So, this is the representation of LQR system in frequency domain we can represent. Our objective here is to determine the gain and the phase margin of this system. So, if system is represented here, what will be my gain margin and the phase margin, that we are trying to find out. So, this we can prove using our ARE. So, consider arithmetic Riccati equation. What is that? This is my PA. So, I write this in the form minus PA minus A prime P plus PB R inverse B prime P minus Q equal to 0. So, nothing but if I will take the minus common, so this will be in the standard form PA plus A prime P minus PB R inverse B prime P plus Q equal to 0. So, this is my matrix difference, arithmetic Riccati equation. So, in this we will add and subtract P into S. So, what we are doing? We are adding PS and subtracting PS. Basically, we are doing PS minus PA, and this PS I am subtracting here PS minus A prime P, and this I will kept as such PB R inverse B prime P minus Q as 0. So, if I will take P common from these two terms, so this is P Si minus A, and from here I will write this as minus Si, because S is a scalar function. So, I can write this as SPS or PS minus A prime, and this P I will write on the right hand side. So, considering these two terms including the negative, this I am writing as P Si minus A, and this I am writing as minus Si minus A prime P, and this I will write as such PB R inverse B prime P minus q equal to 0. So, in this equation we are pre-multiply with and post multiply by Si minus A inverse P. Now, this equation I am pre-multiplying with B prime minus Si minus A prime inverse and post multiplying with Si minus A inverse B. This means this whole equation is pre-multiplied by B prime minus Si minus A prime inverse. This is P Si minus A plus minus Si minus A prime P plus Pb R inverse B prime P minus Q and post multiply with Si minus A inverse B. So, now just pre-multiply and post-multiply this with the, if I will expand this, what I will get? B prime minus Si minus A prime inverse P, this Si minus A inverse, sorry, Si minus A inverse will give me the I and this multiplied with B. So, this is B prime minus Si minus A prime inverse Pb. With second term, if I will multiply, so minus Si minus A inverse, this will give me plus B prime P, these two term will give me B prime P and post multiply with Si minus A inverse B. So, these two term I will get from these two term and here this is multiplied with B prime minus Si minus A prime inverse P B R inverse B prime P minus Q with Si minus A inverse B So, by expanding this we are getting this term. What is Si minus A inverse? Si minus A inverse is the transition matrix, is the state transition matrix. And this we represent as phi s, and so therefore minus Si minus A prime inverse I can represent as phi prime minus S. So, I will use for Si minus A inverse as phi S, which is my state transition matrix, and minus Si minus A prime inverse, this is the transpose, conjugate transpose of my state transition matrix. So, in this term if I will write, I can write this as B prime phi prime S PB plus B prime P phi S B plus, if I am writing this as B prime phi prime minus S PB R inverse B prime P phi S B, and this I am writing Q on the other side as B prime phi prime S Q, this is phi S P. So, by expanding this I am writing Q on right hand side. In this equation had R on both the side, by adding R what actually we will get? We get this PB plus B prime P phi S B plus B prime phi prime minus S PB R inverse B prime P phi S B plus R, and similarly on this side B prime phi prime minus S Q phi S B plus R. So, now the whole equation I can represent by this. So, now we know K equal to minus, my K is R inverse B prime P, or I can write this as R K equal to B prime P and K prime R equal to PB. So, I can use these relations because I know the controller gain K is nothing but my R inverse B prime P. If I will pre-multiply this equation by R, so this is nothing but R K equal to B prime P. If I will take the transpose of this, K prime R equal to PB. So, in this equation I will write PB as K prime R. So, B prime phi prime minus s k prime r for the first term. The second term is b prime p, which I am writing as r k phi s b plus b prime phi prime minus s. Now, see P b is in this equation, P b is k prime r, k prime r. I am writing for P b r inverse as such, b prime p is r k and this I will write as such phi s b plus r, and this side is p prime q phi s b plus r. Now, in this r inverse will become I. So, this is k prime r k So, b prime phi prime minus s k prime r plus r k phi s b plus b prime phi prime minus s, and this I can write k prime r k phi s b phi s b plus r, and this is nothing but equal to my b prime phi prime minus s q phi s b plus r. Now, see in this, if I will consider the left hand side, so this equation I can write in the form as I plus phi prime minus s q phi s b plus r. So, this equation I am writing as I plus k phi minus s b prime b whole transpose, this is the transpose multiplied with the r I plus k phi s b. So, if I will take the transpose and expand this, I will get the same term which I have on this right hand side. So, my overall system can be represented in this particular form, which we can see here. This is nothing but I plus k phi minus s b whole transpose R multiplied with I plus k phi s B equal to B prime phi minus s. So, this equation is called the Kalman equation in the frequency domain. For LQR system, this Kalman equation we can find using our ARE. With the ARE we have got our Kalman equation in the frequency domain, and what is my phi minus s? This is minus Si minus A inverse, phi s is Si minus A inverse. So, another way to represent this equation is I plus k minus Si minus A inverse B R multiplied with the I plus k Si minus A inverse B equal to B prime minus Si minus A prime inverse, which is phi prime minus s multiplied with q Si minus A inverse B plus R. Now, in the next class we will see that how this equation can be utilized to determine the gain margin and the phase margin of a LQR system. So, this class we stop here, and further we will continue our discussion in the next class to determine the gain margin and the phase margin of this LQR system. Thank you very much.